So I'm here to present our work on unobtrusive spatial localization of impact-induced sound waves using 2D beamforming algorithm. It sounds a little daunting, I know. But I just want you to focus on the first term, which is unobtrusive. Unobtrusive meaning sensing from a distance. So you are not just touching the target, meaning, for example, if you take a camera and do some image processing, it will fall under the category of unobtrusive sensing because you are sensing from a distance, right? My name is Rakshit. I'm from India, and I'm working as a scientist at TCS Research for the last 10 years. So this would be the application at mind. One of our sister concerns is Tata Steel, which is like is one of the largest steel plant in Asia. And in a steel plant, there is a machine called a ball mill. So a ball mill is like a giant cylinder, metallic cylinder that rotates, right? So when you mine minerals from mountains, you break the mountains and take everything from there and put it in that metal container. And then you also put giant steel balls and you make everything rotate. And then the grinding process takes action and everything becomes a powder. And then you take that powder and you segregate the mineral out. Of course, I'm oversimplifying things, but this is the process of a ball mill, right? And then there are applications like we have a client partner who runs intercontinental pipelines. So they run more than thousands kilometers at a stretch. And often times there are leaks, and how would you detect those leaks from sound only? These are the problems that we are trying to address here. Now, what happens with a ball mill is that sometimes those steel balls, instead of falling directly on the mineral or the rocks, it directly falls on the metallic liner of the ball mill. And that creates the wearing and the tearing and the ruptures of the metallic sheet, which is like very bad. So from sound, can we do that? So right now the process is there are human beings with trained ears, and they hear the sound and then they change the RPM based on what they hear or what they interfere. So can we do some signal processing on top of that is the challenge, right? So the sensors that are at present is like an accelerometer or a wear sensor or a laser, right? Now they come with their own challenges. Accelerometer and wear sensor, they are contact-based sensors. So you cannot do unobtrusive sensing or sensing from a distance, whereas a laser, it is pretty accurate in terms of finding the wears, but the problem is you cannot roll the thing, right? So it has to be in a stationary mode, and only then you can find whatever you want to find, right? Now let us look at the what literature says. So in literature, there are many good algorithms to find the direction of arrival. So you hear something, you record some sound, from which direction it is coming. There are many algorithms present, but those algorithms work on speech signal, like the way we are talking, and like intermittent sources. So when I say intermittent sources, an example would be the sound that is generated by the engine of an aircraft. These are periodic in nature, but the kind of sound we are looking for is more like impact sound. Like if I do a hammering here, the duration of that sound is pretty small in the time domain, which means in frequency domain it is wide. So I'm talking about non-coherent, aperiodic, and wideband sound sources. And we found that there exists no good algorithm to tackle this sort of problems. So the end objective will be to come up with an algorithm that takes care of the non-contact wideband impact sounds, and we want to do a localization, like in 2D space, where is the sound coming from? So the end objective for a ball mill, a cylindrical structure, would be to come up with this sort of image that gives you, okay, these are the hot spots, like the black stars I'm showing. And if I take the data for like 6 months or 1 year, I know that these are the regions which is getting the impact more than the other regions. So these are the regions which are more prone to breakage, right? So with this mind, we start with the existing algorithms, and the algorithms that are more closer to us were music and spirit. And if I just simplify things, music takes into account the coherence property of the signals, right? So you look at this function. When the signal and the noise subspace are orthogonal to each other, they become ideally zero, but in a real situation, they may not be zero. But this function, whenever they are orthogonal to each other, this will blow up, right? Because it is 1 over something close to 0. Now, if I do an imaging on top of it, And if I give some color depth to it, like background becomes blue, and the more power there is, it becomes red. So you can actually see in a 2D space where the sound is coming from. So this was on the literature. We took that idea, and what we did is, imagine you have an array of sensors. So like M microphones, and there are N sources or N machines at hand. So you take the projection of all the sources to the microphones, and that becomes your steering vector. So all these algorithms, which are meant for narrowband signals, what they do is they steer the vector in across the space, like 360 degrees. But since we are talking about industrial applications, and to our benefit, these machines, when they are set up, they are there for like 100, 150 years. So we know the target. So we are taking the target geometry into account, and we are reducing the search space from 360 degree to only to the target space, right? And then we are collecting the data, breaking it up into small time frames, and doing a bandpass filtering of a pool of narrowband filtering. So we are taking a wideband signal and passing it through a pool of narrowband filtering, and taking the result and then trying to plot it on an image, right? So this was the idea. Now to prove the idea, we took a very, very simple target. The target would be this one. This is a metal plate of 64 by 64 centimeter length and width. That is the sensor prototype. This is the 4 mic array. We do have an 8 mic array now. And that is the signal processing kit. So this thing, we are breaking into 9 subparts, like 1, 2, 3, 4, 5, 6, 7, 8, 9. It's like 3 by 3 matrix. And then we are going to create impacts on those, on that metal plate. So I'm going to play the video. I hope we'll be able to hear the sound. So as you can see, at every position of those 9 locations, we are creating those impact points. So every experiments have 3 trials, and we are going to average the results out. So likewise, for one experiment, we have 27 trials. And this is the result. So this part is your ground truth, and this is the result from our algorithm. Now, the top left, X1, is, you can understand, like for a 3x3 matrix, we are doing the impact sound thrice there, and likewise. And the corresponding results will be this one. So these crosses are the ground truths, and if you can see, like these ones, these white circles is the maximum point of those impact points, right? So when we tried with the existing approach, it is giving us much better result. For example, the X1 case, the impact was top left. Look at the image. The red and yellow portion is coming at top left. Similarly, for the 9th experiment, the impact was done at the right bottom. Similarly, your result is showing here, and the maximum position is here. So this is only the error in terms of RMSE for all the 3 trials combined, right? So that gives us a lot of confidence on the algorithm and the process. So we did a very scientific experiment. So we did 2 trials, one at like 44 centimeter from the target, and the other was 26 centimeter from the target. Of course, the closer you are, the better is your result in terms of RMSE. Now the algorithm or the software that we have created takes care into account of the relative positions of your microphone system and your target. So it is not that you have to keep your microphone just beneath or at some fixed position. You can keep it anywhere. The mathematics will take care of the position. However, there are 2 limitations of the placement. One is you cannot go very, very close to the target, because it is very obvious. If you are really, really close to me, you might not hear what I'm saying. And in signal processing terms, it is called clipping. So the signal clips, so that gives you the lower bound. And you cannot keep a target here and keep the sensor like 3 blocks away from here, because then the sensor will not hear anything. So that gives you the restrictions of the lower limit and the upper limit. But please keep in mind, these are hardware restrictions. So your sensor should be at a position where it can hear properly. So no clipping and no hearing. So with that in mind, we did the test and got the results. And we became a little greedy with the performance. So here, I'm only in the first row. Now I'm doing simultaneous tests. So these are 2 drops of the ball of same dia and same mass. This is our approach. This is one of the algorithms in the literature. Again, these are very beautiful algorithms, but meant for narrowband, like human speak sort of sound, not for impact industrial sounds. And here you can see, if I take into account all the time frames into mind, I'm getting two yellow white dots, meaning two peaks. And if you just look at the image only, the yellow line comes vertically, which is similar to the ground truth, but the literature is going tra-la-la. And then on the second row, we are just going one step further. We are doing the simultaneous test, but this time we are taking two balls of different dia and different mass. The larger cross means it had the higher mass compared to this one. Look at the image. The area of yellow and red is much more than this one. And you could see only one peak. Again, this is not working well. Same experiment, same simultaneous drop test. This had the higher mass. You could see that the area of the red position is much more than this one. Again, this is a comparison with the existing literature, right? So with this in mind, we did the same test on a ball mill, but instead of going to the actual ball mill, we took a very small lab scale ball mill like this one. This is also pertinent to pharmaceutical industries. And we did 3 drop tests, to the left, to the right, and to the center. And this is the kind of results that we got. It actually gave us the left, center, and right. Again, these are not absolute values in nature, meaning I am not able to say at what X and Y those impacts happen, but definitely a relative position we can tell. And from that, the software could give you an image sort of this. Since you know the geometry of the target, you can find these sort of hotspots, right? And if you collect the data for like 6 months, you will know which area is prone to breakage than others. So this was the conclusion, and this is, in a nutshell, the proposed algorithm. The RMSE result was less than 10% in all the cases. And from there, up to this, it was reported in IEEE census, but from here, we have increased quite a bit. This, although is much better than the existing algorithm, but it takes much more time than the existing algorithms, like 21 seconds for one impact. So from there, we have also band limited the filtering, and now we are like 4 to 5 seconds to find one impact position. So I think this is it. Thank you very much for your attention.